Hello guys, welcome to my YouTube channel. You're watching ETA. Now this is the channel whereby we bring you the best of mathematics, physics, and chemistry. Now guys, if you haven't subscribed to my YouTube channel, please do so. And also don't forget to click the notification button and also like my page so that you can get more content when we release. So today I'm going to be teaching you guys a very interesting topic in maths, probability and permutation. Probability and permutation. Let's get right into it. All right. Probability and permutation. Okay. Now, what is probability? Probability is a chance. Probability is a chance. And permutation is the arrangement. All right. Now, this is the arrangement given different combinations. Okay, let's say for instance, if you are given a word bed. Now, if you're given a word bed, how many combinations can we have using these three letters? For instance, we are given the three-letter BAD. How many combinations can we have? The number of combinations that we can have, or the number of permutations that we can have, we're going to have 3 factorials, which is 6. I'm not going to go through how each and every formula was derived. I'm just going to summarize. So the number of combinations that we're going to get, 6. Now, let's say, for instance, if you are given the letter, if you're given the following letters, let's say if you're given MOM. Now, let's say, for instance, number A, if the repeated letters are treated as different letters. Or if they are treated as the same letters. No, different letters. Sorry. If they're treated as different letters, then we're going to apply this rule for number A. Therefore, we have 3 factorial combinations, which is 6. However, if treated as if repeated letters are treated, sorry for that, if repeated letters are treated as though they are the same. Let's see what happens. Now we're diving into a new rule. So what happens is that we get 3 factorials. However, it is divided by the number of repeated and it's given a factorial. The number of letters repeated, and then we give it a factorial. Say for instance, the number of repeated, it's actually m, which is repeated twice. So we're gonna have 3 divided by m, which is repeated twice. It's given an exclamation. Do we have any letter that is repeating? No. Now this will be 6/2, which is 3. So we will have 3 combinations. Now, what happens if we have a lot of repeated letters? A lot of repeated letters. Let me give you an example. A lot of repeated letters. Let's say, for instance, we have a 11 letter word: A, B, R, A, C, A, D, A, B, R, A. Now, this is an 11 letter word. Now, how many combinations or how many permutations are we gonna have? We will have, we have 5 A's in this matter. We have 2 B's. We have 2 R's. By the way, these are not combinations. These are just, I'm just counting the number of letters, 1C and 1D. All right. Now, the number of combinations will be given by the following. The rule still applies. So the number of words are 11. 11 factorial divided by, we have 5 A's. We're gonna have 5 factorial, 2 factorial, 2 factorial. These are, we're actually multiplying all these factorials, by the way. And times 1 factorial times 1 factorial. Now the answer of this will be 8 3160. Now, if we have a situation whereby we have letters that are fixed in position. Now, if we have that, then we have a different story now. Now, whenever there's any letter that is fixed to a certain position, it means its factorial should be omitted. Okay, let's say for instance, we have fixed, if we fix A and D, which is the last, if we fix if we fix, let's say, if you fix the first and the last letters, it means the first and the last letters, these are all A's. So we'll have now 3 A's instead, 3 A's. Then the others will be the same. 2C, 1, no, 2R, sorry for that. Then 1C, 1D. All right. Now our new factorial will, our new permutations will be now the number of letters will change as well. So the n factorial will be 9 factorial. So we'll have 9 factorial because we have reduced by 2. Then 3, 2, 2, 1 factorial, 1 factorial, which will give us 15120. That looks easy, doesn't it? All right. Now, we're gonna move to another instance. Let's say, okay, this was instant C. So our next instant will be B. Now, let's say, for instance, if we have 6 people in the room, if we are permuting the number of objects, but we are combining them in certain groups. So let's say, for instance, if we have 6 people, person A, B, C, D, E, F. and we want you to do to combine and form groups of two. How many groups of two can we form? Okay, now the formula states that we calculate the total number divided by the total number minus the group. Group number. Group amount. Okay. And then we give it factorial. Now, this will be 6 factorial divided by the total 6 minus we're putting them in groups of 2. This will be 6 factorial divided by 4 factorial is given by 30. So we're going to have 30 groups. Now, with permutation, that's just about it. Now, let's move to probabilities. Okay, with probabilities is the number of favorable outcomes. Favorable outcomes. Right. And probability is between 0 and 1. Okay. Now, as I've indicated earlier on, probability is a chance of an event, or it's a chance of a certain outcome to take place. Now, let's say, for instance, if we have a sample S, for instance, if we have a sample, and that sample as 2 events, okay, now if we have 2 events, we're gonna have to consider the regions. Now, this region right here, let me draw properly, guys. Want my things to look a little bit better. No. I want it to be a bit bigger. All right. Now, this region right here, this end, this region here, let's say, for instance, this is event A, this is event B. So this region right here, it is event A. It is event A and event B. So this is where the two, this is where if, for instance, you are picking the samples that are inside event B, if those events are also in event A, this region represents that. Now, we also have another scenario whereby, for instance, we can have that situation there. Now, this region is represented by a union. Now, with the union, this is A and B. This one now is A. No, this is A. Sorry for that. This is A or B. And this one is A and B. All right. Now, these two diagrams are called Venn diagrams. Now, let's do an example. Let's do an example. Okay. Example. A. So let's say we have two events, event A and event B. And we have numbers. And this is the sample. The sample is within this rectangle. All right. 1 is there, 2, 3, 4, 5, 6. Let's say 6 if we put it there. Let's put 7 there and see. And let's just put 8 here. And let's put 10 here. Now, what is the probability of picking an outcome within A? Let us count 1, 2, 3, 4. 4 possible outcomes. So that is 4 out of, we have 10 numbers. 4 out of 10. That's 0.4. Now, what is the chance of picking a number in B? So it will be, we have 1, 2, 3, 4, 5. 5 over 10, which is 0.5. All right, or 1 over 2, either way. What is the probability of picking sample in example within A and B, it will be, it's only one number, it's only two. Two is within event A and B. So we're gonna have 1/10, which is 0.1. Now, what is the possibility of picking a number within A or B? That is, we only have one number outside. So the chances is 9/10, which is 0.9. All right. And that's where it ends. Now, another example. Now, what is the chance of getting 1/6 if you roll a dice? Now, the dice have 6 numbers. So the probability of rolling one or 6, it will be, we're gonna have to add the two probabilities. 2/6, 1/3. All right. Now, there are some definitions that are worth to be noted. Like when there's a mutual exclusive event, and now with a mutual exclusive, if two events don't cross, then that's a mutual exclusive event. However, in the example that we did above, that was a mutual inclusive event, because the two events A and B, they crossed each other. Now, this is a mutual exclusive event. A and B. It's no relationship between event A and B. Now, with a mutual inclusive, it is when the two events cross each other. Now, normally, we have the following symbols. The first symbol, that one, it is the same as and this one is the same as O. Now, in a mutual exclusive event, in a mutual inclusive event, the following formula applies. Probability of getting A plus the probability of getting B minus probability of A A and B. Okay. All right. Now we have the so-called the tree diagram. Okay. Now with the tree diagram, let's say for instance, if we have different events that are independent. We will have, let's say for instance, a coin toss. If you toss a coin, you have two chances. It's either you will flip it and get a head or a tail. The chances of getting a head is 1/2. Tail, same thing, 1/2. Now, if you this is event number 1. Event number 2, if you flip a coin again, you will get the following, get the same results. Is 1/2 chance of getting a head and 1/2 chance of getting a tail. Now, what is the chance of spinning, of tossing the coin and get head on the first event? The second event, you get, say, another head. The probability is 1/2. This is the branch, 1/2 times 1/2. It's given by 1/4. Same thing with if you are tossing to get head, then tail. So it will be head. So for instance, this is the branch. So it will be 1/2 times 1/2. This is where it ends. This is where it ends. This is where it ends. All right, guys, thank you so much for watching my video. If you haven't liked and subscribed to my YouTube channel, please do so. And please go and click the notification button so that you can get more content whenever I upload. Thank you. I'll see you on the next one.